In this video, we're going to discuss molecular orbital theory and the need for it due to faults in hybrid orbital theory. So in hybrid orbital theory, we'd seen things where, say you had dioxygen, O2 and N2. To build it, you'd think about your Lewis structures. I have oxygen. They each have 6 electrons. I would pair. And you'd get dioxygen. And if we did this for nitrogen, 5 electrons, pair, triple bond nitrogen, lone pair. As we look at each of these, the oxygens would look sp2, as they have a lone pair, and a bond. Remember that the second or third bond between two atoms aren't hybrid orbitals. And so each of these would be sp2. If we look at the nitrogen, lone pair, first bond, this would be sp. If we tried to draw them, we'd have the oxygen, we'd have the sigma bond from the hybrid orbital. I would have to have a pi bond caused from the one remaining p orbital. And so sp2 used the s and 2 of the 3 p's. That third p is still available to make the pi bond. For nitrogen, I'd have the sigma orbital overlap where the hybrid orbital is pointed towards each other. And then, I'd have one set of p's that would be on top and bottom. The left and right p had to get used up for the hybrid orbitals so it could point left and right towards the other nitrogen, but the away and towards us is still there. And so you just have 2 sets of overlapping p orbitals. Well, all of these seem to indicate that, hey, there would be an electron and they would pair. There would be an electron and they would pair. And even the hybrid orbital had an electron and paired. The other hybrid orbital, still facing away, going the other direction, has a lone pair in it. And the same's true for oxygen here. It has a hybrid going out a little, hybrid coming towards us. They each have a lone pair. These would each have a lone pair, and there's a hybrid going towards the middle with 1 electron from each forming our sigma. All the electrons are paired. In our Lewis structures, in our hybrid orbital theory structures, all the electrons are paired. This is part of making Lewis structures. However, if you actually experiment with these, oxygen will interact with a magnet. If you pour liquid oxygen over a magnet, it will stick to that magnet, and not like water droplet on a surface tension. It is affected by the magnet. If you pour dinitrogen on a magnet, it goes right through it. What happens is, well, oxygen is not magnetic in the way we think of I can clip it to a fridge or something. It is what we call paramagnetic. Versus dinitrogen, which is diamagnetic. A diamagnetic compound, all electrons are paired. A paramagnetic compound has unpaired electrons, and an unpaired electron can respond to a magnetic field. Like if you have a bunch of magnets and you throw a big one down, the rest will spin around to stick to that new one. A single electron has a magnetic field, but if you put it in a bigger magnetic field, it'll line itself up so that it adjusts to the outside field. So unpaired electrons will respond to outside magnetic field. But they have to have unpaired electrons for this to happen. Dioxygen is paramagnetic, and yet all of our structures seem to say that is impossible. Just for proof, let's watch this quick video. I'm going to jump through it a little bit. They have liquefied oxygen and liquefied nitrogen and this large magnet setup. And they're going to pour liquid dinitrogen, and it falls right through. It is unaffected by the magnets. But if we go ahead and take liquid dioxygen, as soon as it was in contact, it bridged across the two. This is not a surface tension matter. They're far enough apart. This is absolutely because they are responding to the magnet like a needle between two other magnets, where it would line up and connect. So how do we explain it? Well, for that, we're going to dive into the next few parts on molecular orbital theory, or MO theory. Molecular orbital theory takes us one step farther. In atomic orbitals, we said here was a shape so an electron could sit around a single nucleus. In hybrid theory, we said, well, if those electrons are being attracted to multiple nucleus, we need to reach them out in space. They don't really want to take a wave shape built for a single attractive point if they have multiple attractive points. And so we made a hybrid orbital where they could lean out towards another nucleus. But that was still using one atom and just unbalancing its electron shape. MO theory takes this the next step and says, why are we trapping it on one atom? If there are simply multiple attractive locations, why not have a wave that goes over multiple? And so MO theory creates new orbitals that span entire molecules. Let's start with the simplest example. I have two hydrogens. We normally draw them as, hey, here's an electron, here's an electron. We're going to bring them together until they overlap. Well, forget about the electron for a second. Just look at the orbital shape. I have an orbital. They're both positive. They're a wave. Anywhere they overlap constructively interferes and increases the wave there. Well, in 2 dimensions, that's pretty easy to see. We overlap when we say, well, you rise here and you rise here, so really you're going to have that extra rise, and your real wave is the sum of the two. This is harder to show in 3 dimensions as where do you go? It's just more wave in the same spot. We talk about density. Where they overlap, you increase the percentage probability of the electron, or you increase the density of the electron in that location. That just means it's here in the center more often, or more of its charge is there. However you want to think about what the wave represents in terms of charge density or probability. But the idea is it's just there's the electron in between more often. This means that all things given equal, the hydrogen's going to move away some of the time as it's attracted to the electron over here, but it's going to move towards there more of the time as there's more electron density on that side. And this is what holds the hydrogens together. How do we draw that in a way that's meaningful in 2D? Well, we kind of do just show the height increase. If I have 2 spheres and I overlap them, we can draw this as an increase in the middle, sort of using height to represent it. Even though it doesn't really spread out in space, it does show us that there's a greater density in the middle than there is on either side. More chance the electron is here than anywhere else. When I have a hydrogen, and it's 1s, and I have a hydrogen, and it's 1s, they can come together. But there's two ways they can do it. They can be in phase, and when that happens, they overlap in the middle, and you get that increased density. Or they can be out of phase. So this one was plus and plus. You can also get one that's plus and minus. Well, if one is minus, they destroy each other where they overlap. And so I bring a sphere together and I bring another one. This one's plus and minus. They wipe each other out in this location. That section goes to 0. What you actually get then is a shape where there's no chance in the middle. And they wiped out everything that was in the middle. They reach out to the left and the right. Well, one of these shapes puts more density in the center, and one of these puts way less density in the center. In fact, more density is on the outside edges up here. What we've done is we created a node. There was a node there where the two waves destructively interfere. And when I bring these two spherical orbitals together, these are the two possible interactions. Much like hybrid orbitals, when you bring the waves together and create a new one, you create the possible mixes. Two orbitals came in, two orbitals will go out. One of them is that they work together, and one of them is that they work apart. Now, these are still individually symmetric over the whole molecule. We'll see that even though it's really weird to have a gap in the middle, the shape is basically even on the right side as it is on the left. And so the electrons are still centered. We see that down below. There's just as much on the right as on the left. They just preferred to have it in the middle instead of the outsides. Well, curious effects occur here because as our electrons start on our atoms, well, those orbitals are gone. When we bring those hydrogens together, the s orbitals are gone. You can't have an s orbital anymore if you mixed it to make a hybrid orbital. And so our electrons are forced to drop down into our MOs, into the center column here. Well, they're going to go to the lowest orbital first, and the lowest orbital is the bottom one. When your orbitals meet end on end, which a sphere, two spheres meet end on end, or sphere and a p orbital meets end on end, these are sigma. This is a sigma orbital. Truth is, so is the top one. They're end on end. They're just anti-bonding. They put electron density on the outside edge, which would actually pull your molecule apart. So we give them a star. This is anti-bonding. And this one is bonding, because it pulls our atoms together. If we try this with, let's try He2. I have a helium, it's got its 1s, and it has 2 electrons, and I have another helium with its 1s, and it has 2 electrons. When helium overlaps, we get the same possibility. It's just an overlap in phase, or an overlap out of phase. Well, our electrons come in and they start to fall down and they start to fall down. And then they say, well, that orbital's full, but I have to go to MOs. I made MOs. And so the other ones have to go up to an orbital that's actually higher than the original atomic orbital. The net result is that I have 2 electrons trying to pull my molecule together and 2 electrons trying to pull it apart. For this, we need to talk about bond order. Basically, it's the number bonding minus number anti-bonding divided by 2. Well, the bottom one was bonding because it pulled our nuclei together. The top was anti-bonding because it pulled them apart. So 2 minus 2 divided by 2, well, it's 0. Why do you not make dihelium? Why is helium a mono atom? Because it can't. If you try to stick 2 heliums together, the electrons have to go into as many bonding as anti-bonding positions. There's no net attraction, so there's nothing holding 2 heliums together. And so you can't make this. You can, however, make dihelium plus or H2 minus. In both these cases, again, it's going to be the same sigma, sigma star. Overlapping 2 s orbitals is just going to give us the same shapes. And so one of our heliums has 2 electrons and one of our heliums has 1. It's the helium plus. They overlap. They start sharing their electrons to the new shapes. And they run out of electrons at this point. What you find is that there's 2 bonding, 1 anti-bonding. This becomes 1/2. If you ionize helium, shine a bright laser at it, and knock a few electrons off, the helium cation will attach to other helium atoms in the gas. Any that didn't get ionized, they will stick. It's a weak bond. It's only a half order, so it looks like half a bond in strength. But you can make a dihelium cation. There's more bonding overlaps than there is anti-bonding. If you tried this with a Lewis structure, well, helium only has 1 orbital. Helium only has 1. There's no way to bond these. Helium only has a 1s orbital in the Lewis structure. There's no practical way to make a Lewis structure of this molecule. But we definitely can. It's really only done in the gas phase, but we can make it. So molecular orbital theory lets us start to see some molecules that our other theories can't rightly explain. Dihydrogen with an anion, well, again, sigma down, sigma star. You'd have 1 hydrogen with 1. You'd have 1 hydride with 2. They'd start to share their electrons together. What you'll notice is that this ends up looking basically exactly like our helium cation. I've got 2 bonding, 1 anti-bonding divided by 2. It's a bond order of 1/2. Dihydrogen, if we go back and look, dihydrogen only had bonding. It had 2 minus 0 divided by 2. It would have been a bond order of 1. Dihydrogen anion has a half bond order. It's weaker. Adding more electrons to it weakens it, because now those electrons start occupying an orbital that is anti-bonding, that tries to pull the molecule apart. And so here's how molecular orbitals work for overlapping s orbitals. We'll continue with p orbitals and explaining paramagnetism with dioxygen in the next video.